In this lesson, we'll be continuing our discussion about some of the factors that affect whether a substance is a solid, liquid, or a gas at a particular temperature. Specifically, we're looking at how intermolecular forces affect phase changes. So just a quick reminder on how to determine if a molecule is polar or not. So let's consider water. Hopefully you remember that water is polar, and we know that both of the bonds in water are polar. So let's look at how it affects the polarity of the molecule. So when you're trying to evaluate polarity, one of the ways you can do it is you can draw the structure with the appropriate 3D dimension, 3D geometry. In this case, water is AX2E2, which means it has a bent structure. Then you can imagine that you're holding up a mirror plane through the central atom. If you can find a way to hold that mirror plane through the central atom so that it looks different on opposite sides. So here we can see that we have the lone pairs on one side and the hydrogen atoms on the other side. Then you can tell that you have a polar molecule. So because of the asymmetric bent structure of water, water is a polar molecule. And it works out that if you have lone pairs on that central atom, the lone pairs break the symmetry of the molecule, and it causes the molecule to be polar. So it's kind of a cheat of a sort. So let's look at another example. We have carbon dioxide. It has 16 total valence electrons. Remember, you have 4 bonds to carbon. So when you draw the structure, you end up with this, where you have 2 double bonds to carbon, oxygen on either side. Both of the carbon-oxygen double bonds are polar. However, when you imagine that those mirror planes, it doesn't matter where you put those mirror planes, it is always going to be completely symmetric. So because of the symmetry of the molecule, carbon dioxide is nonpolar. And just like with the water, we actually have a little bit of an easy way to get around it. If you're talking about something like a molecule with just hydrogen and carbon, which is what oils are made up of, it is going to be nonpolar. All right, so there was a phrase when I was growing up, is like dissolves like. And I used to think that everybody knew what this meant. And apparently, this is not a common phrase anymore. So what it means is that if you're trying to dissolve something, you need to find a similar solvent in order to dissolve it. So for example, if you got an oil stain in your clothes, you would want to use an oil-based solvent in order to remove it. You wouldn't be able to use water to remove it. So my example is we're going to look at solid iodine. So iodine is iatomic. It's I2, has 14 valence electrons total. So we go ahead and we draw the skeleton structure. That's the octet for iodine, and you end up with this structure. So you say, well, is iodine polar or nonpolar? And you say, well, it's got those lone pairs on it, but the problem is that both atoms are the same type. They're both iodine. So that means that the bond is completely nonpolar. It's completely symmetric. So that means it is going to be a nonpolar molecule. Oops. So if we were to try to figure this out, try to dissolve iodine, we would need to use a presumably nonpolar solvent. So I have found a video that illustrates this. It's by Philip Russell from YouTube, and I have the attribution on the screen there. So we're going to go ahead and watch the video. So here he's got some iodine at the bottom of the test tube. He's got some water at the bottom, and then hexanes, which are nonpolar, in the top. And he's mixing it up very vigorously, which allows the hexanes to come into contact with the iodine. The iodine dissolves into the hexane layer, giving it the characteristic iodine purple color, which is actually kind of a neat demonstration. All right, so intermolecular forces. So whether a substance is a liquid, solid, or gas depends upon the strength of the intermolecular forces keeping those molecules or those particles in close contact with each other. So here we have two molecules, very asymmetric, very polar. This particular molecule is called phenol. I just put a little happy face in the middle of it, just for fun. And right now they are separated enough that there is no interaction between them. They're essentially in the gas phase. And so then we allow them to get a little bit closer. And once they get within a certain distance, the small permanent positive charge on the hydrogen is attracted to the small permanent negative charge on an adjacent oxygen, and they form an intermolecular hydrogen bond. They are now stuck together by those electrostatic forces. So there are a whole bunch of different types of intermolecular interactions depending on if you have mixtures or pure substances. We're just going to limit our discussion to pure substances. So there are three main types. We have intermolecular hydrogen bonding, like we just saw with these phenol molecules. And then we have dipole-dipole. And then we have induced dipole, which is also called London dispersion forces, sometimes van der Waals forces. The easiest way to refer to these last one is just with LDF. So the reason why I have them arranged like that is we have the strongest force at the top, the hydrogen bonding, going down to the weakest force, which is LDF. And the reason why it's important to know these is that if you have hydrogen bonding, the molecules are going to stay stuck together to each other a lot more. So it's going to take a lot more thermal energy to get them to break those intermolecular forces. And so they're going to have higher boiling points than something with really very weak intermolecular forces like LDF. All right, so hydrogen bonding is what you have when you have, well, hydrogen bonding and dipole-dipole are both what you have when you have polar molecules. Hydrogen bonding is a special case of dipole-dipole in that it occurs whenever you have hydrogen chemically bonded to either nitrogen, oxygen, or fluorine. So in this first molecule, we have hydrogen and fluorine in the same molecule, and the molecule is definitely polar, but they are not chemically bonded to each other. So this one would only have dipole-dipole interactions. It would not have hydrogen bonding. In the next one, we have methanol, which is a similar structure, but it has hydrogen chemically bonded to oxygen. So when these molecules are close enough together to form those intermolecular hydrogen bonds, which are always shown with a dashed line, because they're almost like a chemical bond, but they're 10 times weaker, then this will actually have the hydrogen bonding. Dipole-dipole is when you have polar molecules that do not have hydrogen bonding. So they don't have one of the hydrogen chemically bonded to nitrogen, oxygen, or fluorine. And so I just looked up another example. So hydrogen fluoride would be an example of a polar molecule that would have hydrogen bonding. It has a boiling point of 19.5 degrees C. Whereas hydrogen chloride, even though it's just one level down and a little bit heavier, but not excessively so, it is still polar, but it is only dipole-dipole because it's not one of those magic three. So it has a boiling point of minus 85 degrees C. So dipole-dipole is substantially weaker than hydrogen bonding. So the last one is induced dipole. It's a little difficult to kind of get an understanding of this since it's talking about nonpolar molecules only. So when you have large nonpolar molecules, you're also going to have a large electron cloud around it. So in the example, I have C6H14. Now these electron clouds are not stationary. They are constantly moving around, responding to the different factors from the surroundings. So say something causes this molecule on the right to be temporarily polarized. So all of the electrons, not all of them, but the electrons start concentrating just a little bit down on the right-hand end. And so now we got an increased negative end. When you say the blue means more negative, which leaves the other end being slightly more positive. Now that polarization of the molecule will induce a polarization in an adjacent molecule. But since it's just temporary, the electrons can go back to being more or less symmetrically distributed, and then maybe they end up being polarized in the opposite direction. So this kind of goes back and forth. So with nonpolar molecules, the only intermolecular force they have is LDF, and this pretty much means that the boiling point for these is going to increase with the molar mass of the molecule. I always tell my students that the best way to understand this is that if you just imagine you're trying to throw a bowling ball versus a basketball, they're both about the same size, diameter, but it takes a lot more energy to get the heavy bowling ball up into the air, which we're going to say is like the gas phase, as compared to getting the basketball up into the air, which would be, again, like the gas phase. So that would be it. Thank you for listening.